Okay, hi everyone, and a warm welcome to the official YouTube channel of EduShort for your UGC NET JRF Economics preparation. So, if you have seen the previous video that I have uploaded, there we have started discussing about unit number 3, which is statistics and econometrics section for your paper 2 of UGC NET examination. And in the previous class, we have discussed 25 most important questions that could be asked in your exam from the statistics and econometrics section, right? So we have already discussed that. If you haven't watched that video, please check that out. And after watching that, come back to this video. This is going to be part 2 of our discussion, where we again going to solve some of the most important questions. Today's emphasis is on econometrics. In the previous class, we have talked about statistics and a little bit of econometrics, but this video is going to be dedicated to only econometrics section, and we will see some of the most important topics and questions from that, right? So I'll solve questions. Along with that, I'll also discuss the important points associated with it, right? So this is the agenda. So let's take a look at the first question. This is June 2012 paper. It says, which of the following statement is not correct in the presence of heteroscedasticity? So basically, in econometrics, what is important in your UGC net is firstly, thoroughly go through what is the classical linear regression model and also understand in depth what are the different assumptions of those models, right? In the paid batch, we discuss those things in details. So see, in case of classical linear regression model, there are few assumptions which are very important. We will solve questions on that also. And the next thing that is important is the violations of the assumption of the classical linear regression model, where the concepts of this heteroscedasticity, autocorrelation, multicollinearity, simultaneity bias, all these things come into picture. So one of the most important violations of classical linear regression model is heteroscedasticity, which basically means the error variance is not constant. Error variance varies across the explanatory variable or the observations that you take into account. That is heteroscedasticity. Now, what will be the consequences? In all these violations, what you have to know, first thing is that what is the concept, why this happens, what is the violation, then you have to know what will be the consequences. If heteroscedasticity is present, what will happen to the model? If autocorrelation present, what will happen to the model? If multicollinearity is present, what will be the consequences? So this has to be, gone through in depth. That is very important. And the third thing that you need to know, what are the remedial measures, right? If heteroscedasticity is present, how will you handle that? And same for all the other things, right? So these three things you have to prepare in depth, right? So in our particular question, what will be, they are asking about the consequence of heteroscedasticity. So the best way to remember this thing is that under heteroscedasticity, the OLS estimates will still be unbiased, they will be consistent, but they will be inefficient. Remembering this pattern, that if heteroscedasticity is present, the estimators will be unbiased, they will be consistent, but they will be inefficient. Inefficient means the minimum variance property will not hold. The other things will be holding. Under autocorrelation, same thing. Unbiasedness will be there, consistency will hold, and inefficiency will be there. Same as heteroscedasticity. Under multicollinearity, what will happen? Unbiased, consistent, as well as efficient. Right? So these are the three things that you have to remember very clearly. And this is the best way to remember this, right? So let us see. First option, heteroscedasticity does not alter the unbiasedness and the consistency property, which is absolutely true. That is what we discussed, that unbiasedness consistency holds. Second option is saying OLS estimators are of minimum variance or are efficient. So efficiency is not holding, it is inefficient. That is why it is a wrong statement. And that is what we have to find out. We have to find out all the incorrect statements. So this will be one of the statements. Third property, blue estimators are provided by the method of weighted least square. That is also true. In case of heteroscedasticity, in presence of heteroscedasticity, weighted least square and generalized least square, these are the methods that we frequently use. The OLS method will not give you efficient estimator. That is why this is also true statement. That is why this is not an answer. And the fourth is T and F test based on the standard assumptions of the classical linear regression model may not be reliable. So that is also true. Since I have told you that minimum variance is not holding, that is why the variance, the error variance Error variance suffers from heteroscedasticity. That is why the estimators will have inefficiency in them. Minimum variance is not holding. That is why the standard error that you will calculate from the variance, that will also be not reliable. And if the standard errors are not reliable, then the t statistic, if statistic, whatever you compute, that will also give you misleading answers. That is why all the tests, either it is t test or it is f test, all the tests will give you misleading answers if heteroscedasticity is present in your model. So what will be the right answer? Right answer will be option B. You have to find out all the incorrect statements, incorrect consequences. The only incorrect consequences OLS estimators are minimum variance or they are efficient, which is not true. They are inefficient in nature, right? So B will be the right answer for this question. So this is June 2012. Now let's move on. This is December 2012, match list 1 and list 2. See, the first question is saying Durbin-Watson D statistic. Durbin-Watson test is a very, very, very important test that detects the serial correlation or the autocorrelation. Serial correlation is another name for autocorrelation. So A will be option number 3. R square. R square is the coefficient of determination. R square basically measures the total variation. How much percentage of the total variation of the model is explained by the independent variables or the explanatory variables or the regressors of your model. So that is also known as the goodness of fit measure, right? R square is known as the goodness of fit measure. So B will be option number 4. Now option C is Dickey-Fuller test. Dickey-Fuller test is used to measure stationarity. Dickey-Fuller test is a stationarity is a time series concept. So basically what we say is that when is a process stationary? In case of time series process, in time series we write the, the model as the processes. You have auto-regressive process, various kinds of moving average process, various kinds of processes are there. So when will you call a process to be stationary? A process will be called stationary if the statistical properties of those processes are independent of time. What could be the statistical properties? It could be the expectation, it could be the variance, and it could be the auto covariance, right? So expectation, variance, and auto covariance. These are the few statistical properties. If you see the values of those measures are independent of time, they are not changing over time, then you will say the process is stationary. So I'll take separate class on time series and the rest of the topics probably in the next class or some other classes. So I'll discuss that in that video, right? So Dickey-Fuller test is a very important test which is used to measure stationarity, which is used to check if the time series is stationary or not. So that is why C will be 1. And finally, you have the dummy variable. What is dummy variable? Suppose you want to introduce qualitative data in your model. Qualitative variable in your model. Qualitative means categorical variable. Categorical means which you cannot express in numbers. For example, gender. Gender is a qualitative variable. You male, female, or other. So you cannot express them as numbers. That is why you have to introduce dummy variable in order to introduce them in your model. Similarly, what could be other thing? Mother tongue. Your mother tongue is also another thing. Suppose the season, winter, summer, right, autumn, spring, they are all the seasons. Season is also a qualitative variable. So in case of qualitative variables, that those variables which you cannot express using numbers, in that case, you have to introduce some variables that is known as the dummy variables, right? So dummy variable will be associated with qualitative effects. So what will be the right answer? A is option number 3, B4, C1 and B2. So B will be the right answer for this question. This is December 2012. Okay. So let us go to June 2014 now. Which of the following assumptions are required to show consistency, unbiasedness, and efficiency of the OLS system? So please remember this thing as a thumb rule that the normality assumption of the error term is only required when you test hypothesis. So this normality assumption that you do, this is only for statistical inference and hypothesis testing. And for all the other cases, for measuring consistency, unbiasedness, efficiency, the rest of the 3 properties has to be satisfied. So these are all the CLRM assumptions if you look at it. So this normality is not one of the CLRM assumptions. This is specifically made for testing the hypothesis. This is not a usual CLRM assumption. So the rest of the assumptions that are written here, the expectation of the error term has to be 0. Variance of the error term. So this is basically required for unbiased. And the rest of the 2 are required for consistency and efficiency. Right? Error term, expectation of the error term 0, it is required for checking the unbiasedness property. Variance of UT is 0. UT is basically the error term, stochastic error term in your model. And there is no autocorrelation. So no heteroscedasticity, that is homoscedasticity, and non-autocorrelation. These assumptions are required for testing consistency and efficiency in your model. And the first assumption is required for unbiasedness of your model. Only the fourth assumption, that is the normality assumption, this is only introduced when you want to test hypothesis and nothing else, right? So keep this in your mind. It's very important to remember. So what will be the right answer? The question says, which of the following are required to show consistency, unbiasedness, efficiency? So A, B, and C, all three are required, right? So all the three, 1, 2, and 3, all the three will be required. Only the fourth is not required. Fourth is not required above, right? So C will be the right answer. So 1, 2, and 3, all the three assumptions. Again, I am repeating that CLRM assumptions are very important. We can give you questions from any direction, right? So please keep that in mind and prepare them. Right? Next question, June 2015. The term best in the best linear unbiased estimator, or the blue, that we call it as blue, implies what? So best means minimum variance. Best, when you call the estimators to be best, when it has minimum variance. So this is also a very important question. So it will be minimum variance of estimator. So it is basically following the Gauss-Markov theorem. What is Gauss-Markov theorem? In Gauss-Markov theorem, it is stated that if all the classical linear regression model assumptions follows, if all the assumptions hold, then the estimators that you will get from the OLS, applying OLS, that will give you the blue estimators. That is, they will be best linear unbiased estimator. Best means, as I've told you, minimum variance. Linear will be, the estimators will be linear in terms of Y, that is the dependent variable, right? Or the regressant dependent variable. Unbiased means the expected value of the expected value of the estimators will be actually equals to the true population parameter. That is unbiasedness. So best, linear, and unbiased, these three properties will be whole under Gauss-Markov theorem if all the CLRM assumptions, right? You have 6 to 7 CLRM assumptions. If all those assumptions hold, then the OLS estimator in two variable regression model, if you apply OLS assumption, if you apply OLS estimation process, then the estimator, the estimated values that you will get will satisfy all the three properties. It will be best, means it will have minimum variance. It will be linear in Y, that is linear independent variable, and also it will satisfy the unbiasedness property, which basically means the expected value of the parameter will be equals to the true population, right? So true population parameter. So that is the thing. So B will be the right answer for this question. Quickly see the next question. December 2015. Now you are given a multiple linear regression model, MLRM. Next important topic. MLRM is the next important topic. Here you see only one dependent variable, but you have k number of independent variable or the regressors. 1, 2, up to k. Now, how many parameters are there in this model? If you see, beta naught is the intercept parameter, and beta 1, beta 2, up to beta k, they are the slope parameters. So altogether, how many parameters are there? Beta 1 to beta k, you have k parameters and plus 1 intercept parameter. So you have k plus 1 parameters in your model, right? MLRM model. Now, the question asks, then the degree of freedom of the test statistic with n number of observations will be what? Now, understand what is degrees of freedom. Degrees of freedom means how many variables or how many, not variables, how many observations are free. Degrees of freedom. Freedom means how many observations among the n number of observations are not having any sort of restrictions. Now, what do I mean by restriction? Restrictions means parameter estimation. So let me write it down, then I'll explain. So total number of observations minus the total number of restrictions. Right? This is the simple concept of degrees of freedom. Now, total observation is simple n, which is given to you. There are n number of observations. Now, as I've told you, total restrictions means how many parameters are in your model which you need to estimate. And why this is restriction? Because if you remember, in case of OLS, what we do, we form the normal equations, right? What we do, we form normal equations. So if you consider only two variable model, you have two parameters. So if you consider only this much, this is what is the two variable simple linear regression model. You have two parameters, namely one slope parameter, one intercept parameter. And if you know the process in OLS, what we do, we form two normal equations. So whenever you have two parameters, we have two normal equations, and normal equations are nothing but restrictions, right? Normal equations are, so you have to follow these two specific equations in order to estimate those parameters. So they are basically restrictions. Whenever you have a specific relationship in terms of normal equation, they are regarded as restrictions basically. So for two parameters, you have two normal equations. So for k plus one number of parameters, how many normal equations will we have? K plus one. So number of parameters will be equals to the number of restrictions. So your total restrictions will be simply k plus one, right? So degrees of freedom, you have to calculate what will be the degrees of freedom for the test statistic T. So degrees of freedom will be simply this. Total observation is n minus total restriction. That will be simply given by the total number of parameters in your model, because that many normal equations you will have and those many restrictions you will have. So it will be simply n minus k minus 1, right? So n minus k minus 1, C will be the right answer for this question. Okay. Now let's move to the next question. July 2016. So I have basically taken from 2012 to 2024 questions, most important questions. And these are the important topics. I will try to cover all the important topics here. So see the next topic, consider the two regression models. Now we are considering two regression models. In the first model, you have only one explanatory variable. In the second model, you have two explanatory variables. Now you have to say which of the following statements are true. There is a concept. This is the concept of R square and adjusted R square. Now, if you remember the concept, so why do we need adjusted R square? We need adjusted R square because R square has a serious drawback. What is that? R square is non-decreasing in the number of explanatory variables in your model. What does this mean? So it basically means if you keep on adding new explanatory variables in your model, right? As you keep on adding new explanatory variables in your model, your R square will always increase. It will always increase. It is non-decreasing means it will always increase, right? If you include the variables, explanatory variables in your model, your R square always increases. But it could be so that some of these variables are not statistically significant. They could be statistically insignificant. But R square denies this fact. That is the severe drawback. What I'm trying to say is that suppose you x1 is already there, you add two more extra variables, x2 and x3. Suppose, for example, now you see both these variables, both of these explanatory variables are statistically insignificant. Insignificant means what? The coefficient that they have, suppose beta 1 and beta 2, the coefficients that is attached with them, they are essentially equals to 0. That is what the insignificance means. If they're insignificant, means the coefficient is 0. Basically, it means they are unable to explain any variation of the dependent variable. If this is the scenario, then also R square will increase. R square is basically what? Goodness of fit. So it basically implies the total variation of the dependent variable, which can be explained by the independent variable. Now, if these two variables are essentially insignificant, should the R square increase? Are we able to explain more variation or not? Essentially we are not getting any more variation, right? If these two variables are statistically insignificant, we are unable to explain any more variation, but still R square increases. Still R square increases. That is the problem. That is why we have to adjust R square with the degrees of freedom. So degrees of freedom, again, the restriction. Degrees of freedom means the restriction. So in case of adjusted R square, that is what we do. We adjust the R square with the respective degrees of freedom. That is why R bar square can be negative as well. So they basically take into account the insignificance of variable. So if you keep on adding new variable, R bar square might fall, right? R square cannot fall anytime, but R bar square can fall. It might capture the insignificance of your explanatory variable, right? That is the main funda of R square and R bar square. Now see which statements will be true. First option says model 2 must have an R square at least as high as model 1. See, model 2 has two independent variables, model 1 has one independent variable. As I've told you, if you keep on adding variables, R square will always increase. So this statement is absolutely true that model 2 must have as much R square. So R square will be definitely higher than the model 1, or it will be at least similar. It cannot decrease. It cannot decrease. Though we don't know, should we add this variable or not, we don't know the significance of this x3 variable. Still, if you find out R square, that will increase. It is non-decreasing. Remember this fact, you can note it down. R square is always non-decreasing in the number of explanatory variables. That is why if you keep on adding variables, R square is always. So that this statement is true, that model 2 must have R square at least as high as that of model 1, right? Now the next point is saying model 2 must have an adjusted R square at least as high as model 1. Can it be true? If you understood what I have explained before solving this question, you will know this is not true. Because in adjusted R square is a measure that is introduced to handle this problem. So adjusted R square may not be as high as model 1, right? Because we don't know the significance of this. It might decrease also. Adjusted R square can be strictly less than the R square also in this. Number three, C, model 1 and 2 would have identical values of R square if the estimated coefficient alpha 3 is 0. This is true. See, if we know that this is 0, right? If this, we already know that this variable is insignificant. Alpha 3 0 means this variable is insignificant. So essentially you have only one explanatory variable. So the R square that you calculate from this particular model will be just equals to the R square that you calculate from this particular model, right? So that is what is written here. Model 1 and 2 will have identical values of R square if alpha 3 is 0. So A and C both are true. Option D, model 1 and 2 would have identical value of adjusted R square. Again, adjusted R square, we cannot say anything, even if alpha 3 is B. So what will be the right answers for this question? The right answers will be A and C. So we can only comment on R square. We don't know about adjusted R square. Adjusted R square can go to negative as well. It can be equal to R square as well. It can be more than R square. So basically the relationship, you have to find that out in specific cases. You cannot comment on adjusted R square. You can only say about R square. So A and C only will be the right answer for this question. So please understand, if you don't know the concept of R square and adjusted R square, please make yourself familiar with that, because this is a very important concept in econometrics. Next question, November 2017. If a Darwin-Watson statistic takes a value close to 0, what will be the value of the first order autocorrelation coefficient? So as I've told you, Darwin-Watson is a very important test which is used to measure first order autocorrelation. Darwin-Watson is only applicable for the first order autoregressive process. What is first order? Means the maximum lag value. The maximum lag value that the process will have, that is only 1. So if the maximum lag value increases to 2, 3, 4, the order also increases to 2, 3, 4, and so on and so on, right? So basically, if the maximum lag value that you have in your autoregressive process is 1, then you will say, then you can apply Darwin-Watson. Now, there is a relationship between this Darwin-Watson D statistic and the autocorrelation coefficient of the first order. And it is very essential for you to remember. Let me write it down. D is the statistic value, Darwin-Watson statistic is related to the first order autocorrelation. This is the relationship. See, this is very, 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 very important thing. D is the D statistic, Darwin-Watson statistic value. It is related, it is rho cap. Rho cap represents this autocorrelation coefficient. First order autocorrelation coefficient is given as this, right? If this is the scenario, now it is said that Darwin-Watson P statistic value is 0. So put D equals to 0. So just find out what will be rho cap. So this 2 will be here going to 0. So 1 minus rho cap will be 0. So the first order autocorrelation coefficient will be plus 1. So it will be close to plus 1. If D is going towards 0, rho cap is going towards plus 1. So it will be close to plus 1. Essentially, you need to understand 3 values. Mainly question might come from 3 values. This is what we understood, that if D is 0, the rho cap will be exactly plus 1. Now you have to know if the value of D is 2, exactly equals to 2, then what will happen from this equation? See, 2 equals to 2, 1 minus rho cap. So this 2 and 2 is gone. So here it will be 1. So rho cap will be exactly equals to 0. So there is no autocorrelation at all. If D is 0, then there is perfectly positive autocorrelation. This is the perfectly positive autocorrelation. And now if D is equals to exactly 0, then there is no autocorrelation. And another value would be when D equals to 4. You can calculate this. If D equals to 4, what will be this? This is 2. So now 1 minus rho cap equals to 2. So rho cap will be equals to minus 1. So this will be perfectly negative autocorrelation. Perfectly negative autocorrelation. So these are the three values that you have to essentially remember. What will happen when D takes the value or D approaches to 2? What will happen to D approaches to 0? And what will happen when D approaches to 4? So what we have seen is that if D approaches to 2, there is no autocorrelation. You can just note it down as your thumb rule. You can write it down in your notebook. When D tends to 0, which is the question here, which has been asked in November 2017, when D tends to 0, there is perfectly positive autocorrelation. Perfectly. +1 means perfectly positive. And when D goes to tends to 4, the value 4, there is perfectly negative autocorrelation, right? So these are the three values that question might be asked from. And this is the relationship which you have to know. This is the relationship between D statistic and the autocorrelation coefficient. And remember, this is only applicable for the first order. So any other order they give you, then you will have to say D statistic, the Darwin-Watson test is invalid. Darwin-Watson test can only be applied for the first order autoregressive process, right? I hope this is clear. Let's move to 2018 December paper. In regression analysis, if a quantitative variable has m categories, one can introduce how many dummy variables? So this is also an important concept of dummy variable. As I've told you, dummy variable previously what I've told, it is used for qualitative variables. Qualitative means categorical variables which we cannot, introduce numbers, which you cannot express as numbers. For example, the season. So there could be, what could be the seasons? It could be spring, it could be summer, it could be winter, it could be autumn, right? So there are, suppose these 4 seasons are there. So if season is a variable which has m number of categories, season is a variable which has m categories. So m is how much? 1, 2, 3, 4. The value of m is 4. Season is a categorical variable. Season is a categorical variable or it should be qualitative variable, not quantitative. Sorry for that. So it should be qualitative variable or categorical variable. So it has n categories. So 1, 2, 3, 4 m categories are there. So how many dummies should you introduce for m categories? You will introduce m minus 1 dummy variable. This is also an important concept. You will only introduce m minus 1. So you will introduce one less than the total number of categories that are there. Why this is so? We want to avoid something called dummy variable trap. There is a concept of dummy variable trap. I know you guys have heard this thing. What is dummy variable trap? In econometrics, you can prove this thing that if you have suppose m number of categories, and if you introduce m number of dummy variables in your model, then there will be multi-collinearity problem. Then there will be perfect multi-collinearity problem in your model. And if perfect multi-collinearity is present, then you cannot estimate all the parameters separately. This is one of the consequences of presence of multi-collinearity. So multi-collinearity is present, it will, restrict you to estimate all the parameters individually. You can find out the joint effect of the parameters, but individual effects cannot be found out. So that is why that is the dummy variable trap. In order to avoid that trap, you have to introduce one less dummy. So that is the important question, and A will be the right answer. So read about dummy variable trap. So dummy variable trap, in order to avoid this, you have to introduce one less dummy than the number of categories that are there in your model. Right? This is done. July 2018. Generalized least square method of estimation will be suitable for which of the following problems? Remember this thing that GLS and the weighted least square, these two methods are suitable only for autocorrelation and heteroscedasticity. Only for autocorrelation and heteroscedasticity, GLS and WLS methods will be valid. Remember this thing. And for multicollinearity, we need other measures like ridge regression, principal component analysis, right? These are the two basic methods that we use to handle multicollinearity. Remember this, ridge regression and principal component analysis, PCA, what we call in short, is used for multicollinearity. And for errors in variables, we usually use other measures like instrumental variable and so, right? There are other measures that help you to handle this. So instrumental variable is the main method to handle that. So multicollinearity and errors in variables, in these two scenarios, generalized least square method is not helpful. So A and B only will be the right answer, right? So generalized least square is used for autocorrelation and heteroscedasticity. So in the presence of autocorrelation and heteroscedasticity, generalized least square will ensure efficient, consistent, and unbiased estimator. right? If autocorrelation and heteroscedasticity is present, then we know in both of the cases inefficient estimate. If you apply OLS in a model which has autocorrelation or heteroscedasticity, then the estimators will originally be inefficient. So in order to handle that problem, in order to tackle that problem, if you apply generalized least square, then that problem can be solved, right? If in generalized least square will give you efficient outcome. Unbiasedness consistency to maintain हो ही रहा है, तो efficient outcome can also be ensured under these kind of problems, right? So these A and B will be the right answer for this problem. Let's quickly see some more problems are there. Let us quickly do that. June 2019, match the list. Gauss Markov. Gauss Markov, I've already explained. Gauss Markov will give you the blue estimators under CLRM assumption. If CLRM assumption follows, Gauss Markov will ensure blue properties. Coefficient of determination is given by R squared. This is also known as the goodness of fit, which we have discussed. Now see, this is the individual coefficient test, individual test. Beta 2 equals to 0 against the alternative beta 2 not equals to 0. It will be not equals to 0 basically. A printing mistake is there. So that will be one-sided test. Okay, so it will not be that. Sorry. Sure, I think there is some mistake is there. So if it is one-sided test, so what will happen? In case of one-sided test, if beta 2 equals to 0 is the null hypothesis, alternative can be either beta 2 greater than 0. This could be one alternative, or beta 2 can be less than 0. These are the two alternatives that will give you the one-sided test. And two-sided test means that beta 2 not equals to 0. Two-tailed test. This is two-tailed test and the rest of the two are one-tailed test, right? So here there is some mistake, but the answer will be that there is no other options similar to that. And heteroscedasticity is checked using the Goldfield quantity. So autocorrelation is checked using the Darwin-Watson test, and heteroscedasticity is checked using the Goldfield quant test, right? So D will be option number 3. Now match here. A is 4, B1, C2, and B3. So A will be the right answer. June 2019 paper, applying OLS to the simultaneous equation. So I have touched upon all the concepts one by one. If you have noticed that applying OLS to simultaneous equation results in the parameters being what? So in case of simultaneous equations, what happens is that something called simultaneity bias takes place. Simultaneity bias, what is that? Simultaneity bias means the explanatory variables in your model are correlated with the error term. So the problem of endogeneity arises. Endogeneity leads to simultaneous bias. So if simultaneity bias exists in your model, that is problem of endogeneity exists. In that case, in those models, if you apply OLS, what will happen? You will get biased and inconsistent estimates. So in case of simultaneous equation, you cannot apply OLS. You can never apply OLS. This just keep it inside your head. It's very important to remember that if simultaneous equation is there, simultaneous means bivariate causality, bidirectional causality exists. So basically X causes Y and Y causes X. If this is the kind of scenario, then what happens is that the explanatory variables in your model gets correlated with the error term, which is strictly a violation of assumption of CLRM, if you remember, right? In CLRM, what we do, exogenity assumption has to be maintained for CLRM. That explanatory variables has no correlation at all with the error term. But if the correlation arises, that is, they get correlated, explanatory variables with the error terms, then the problem of endogeneity arises, which leads to something called simultaneity bias, that is due to this bidirectional causality. And in those models, if you apply OLS, the estimators that you will get will be biased and inconsistent. Bias means what? The expected value will not be equals to the true population parameter. That is the biasness. And inconsistency means as your sample size grows, then also the bias is not eliminated. Right? Inconsistency means what? If you increase the sample size, if your sample size goes towards the population size, then usually what happens? The bias gets eliminated. But here, if simultaneous equation is there and you are applying OLS, your sample size grows, but the bias that you have, simultaneity bias that you have, that does not go away. Or the biasness of the estimator that you have, that does not go away. That is why inconsistency also arises, and it is also inefficient. So biasness, inconsistency, inefficiency, all the things will be there. So just remember this thing. Applying OLS to simultaneous equation leads to biasness of the estimator, inconsistency, and that will again reinforce inefficiency in your model. So you cannot never ever you can apply OLS to the simultaneous equation model. What are the alternative approach? Basically, we use the two-stage least square method. Right? Two-stage least square method is an alternative, and there are several other alternatives also. You can study this thing a bit. To two-stage least square instrumental variables and two-stage least square. These are the two basic methods that we use generally in real life scenarios. That are the best alternative methods that you can use if simultaneous equation are present, because they address the endogeneity problem. That is why they give you efficient estimators or consistent and unbiased estimators in the presence of simultaneous bias. So this is also another important concept. Let's do the next question. So in case of multiple, this is March 2023, in multiple linear regression model like this, so again, see k plus 1 parameters are there. If you want to test the joint significance, so for individual significance, we always use t-test. That is, if you want to find out the significance of a particular coefficient, beta 1 equals to 0, beta 1 not equals to 0. If you form the the hypothesis like that, that will be individual test that you can perform for all these individual parameters. But what happens if you take two parameters at once, so beta 2 and beta 3, you want to find out the joint significance. This is known as the joint significance, right? If you want to measure the joint significance, then where this is the null hypothesis, and the alternative is at least one of them is non-zero, at least beta 2 or beta 3, one of them is non-zero. Then in that case, what test that you will use? That you will always use the F test. T test is used for individual significance, and F test is used for joint significance. That is the main motive of giving you this question. Remember this thing. And chi-square test and ANOVA, these have separate significance. Chi-square test we use for categorical variables. This is also another question that has been asked in UGC NET. I think we have done this question in the previous class, I hope. So chi-square test is used for categorical data or categorical variable. When categorical means again the qualitative variable. Right? If qualitative variables are present in your model, you can use the chi-square test to find out significance and not the regression coefficients. T-test is used for individual regression coefficients. F-test is for joint significance. And ANOVA is a different thing. It is used to compare the mean values of two or more groups. It is not about the regression coefficients at all. So ANOVA is out. ANOVA is for comparing the means of two or more groups. Chi-square test is used to find out significance of the categorical variables particularly, right? So here the answer will be option number D. Let's see the last two questions. This is the second last question, June 2023 paper. It says, which of the following are not symptoms of multicollinearity? So basically, how do you identify whether multicollinearity or is present in your model or not? How do you identify that? There are some thumb rules. What are the thumb rules? High R square and few significant T ratios, which is point number 1. See, high R square with few significant T ratios for the coefficient. This is one of the thumb rules. If this is present in your model, you can be 100% sure that multicollinearity exists. So A is definitely true. Second point is saying high pairwise correlation. That is also true. What is multicollinearity? Multicollinearity means the explanatory variables are correlated with each other. So if you take pairwise correlation, definitely the pairwise correlation will come out to be very high. So this B option is also true. T, tolerance coefficient value, tolerance value is close to 0. What is tolerance? Tolerance is basically 1 upon the VIF. Now, what is VIF? VIF is the variance inflation factor. This is the main, metric that helps you to understand multicollinearity. If the VIF value is greater than 10, this is basically showing the variance of the estimator. So alpha, beta, suppose you have two parameters, you find out alpha, variance of alpha and variance of beta. So if multicollinearity is present, your variance will always be inflated. You will get higher variance than usual. Right? The variance will be minimum, but the variance, they are efficient, but the variance values will be very high, exceedingly high. So if the variance inflation factor in that way, if you find out if the value is strictly greater than 10, you will say that yes, multicollinearity is present in my model. Now, the more the variance inflation factor, the more will be the stronger, the strength of the multicollinearity will increase. So see, the tolerance factor is simply the reverse of that, 1 upon the variance inflation factor. So what should be the value of this? So if VIF goes to infinity, it starts a strong multicollinearity. So 1 upon this will, if it goes to 0, if the denominator goes to infinity means 1 upon that will goes to 0. If tolerance factor goes to 0, that will imply multicollinearity is present. So that is what is the third point. See, tolerance value close to 0, that will also signify multicollinearity is present in your model. The final two factors, see, variance inflation factor, as I've told you, is below 10. The answer is no, as I've told you. This value has to be strictly greater than 10. This is one of the clearest indication of multicollinearity. And the last point is tolerance value close to 1. This is also not true. Tolerance value has to be close to 0 in order to have multicollinearity. So what are the right answers? A, B, and C. So okay, so you have to find out which are not the symptoms. See, the question says which of the following are not the symptoms of multicollinearity. So only D and E, they are not the symptoms. So D and E will be the right answer. So please read the question carefully. Don't make the mistake that I did. So not the symptoms means D and E, they are not the symptoms. Rest of the things indicates, clearly indicates presence of multicollinearity in your model, right? And now the final question that we have is this. June 2024 recent question. In a two variable regression model with 13 observations. So n is given to you as 13. The variance of the error term, error variance, which basically means sigma cap square. If you remember, we have talked about this sigma cap square, 0.893652. This is given to you. Total sum of square is given to you, TSS, 1051188. Then you have to find out the coefficient of determination. So coefficient of determination is what? Simply ESS upon TSS. So essentially, you have to find out the value of ESS, right? ESS is given to you. If you know ESS, then you can compute R square. So for that, how will you find that out? Firstly, find out what is RSS. If you remember, RSS formula is sigma cap square upon n minus 2, right? Do you remember this formula? We have, derived this in class. If you know this thing, very important property. So why this is n minus 2? Because we are considering a two variable model. If this is three variable, then you will write n minus 3 here. If it is four variable model, you will write n minus 4 here. In general, if it is k variable model, you will write n minus k here. That is the formula. Now sigma cap square is given, n is given, so you can find out what will be the value of RSS. So, okay, so the formula is this. Sigma cap square should be RSS upon n minus 2. Sorry for that. I have written it wrongly. This is the formula, right? Sigma cap square, the estimated value of the error variance, that is basically RSS upon n minus 2. That was my mistake, right? RSS upon n minus 2. So what will be RSS? It will be simply n minus 2 into sigma cap square. Now you have value of n, value of sigma cap square. N is what? 13. So 13 minus 2, that is 11 into sigma cap square. Now let us calculate this. Let me use a calculator. 11 into 0.893652. 3652, yes. So the RSS will come out to be 9.830170. This will be the value of RSS. Now from the decomposition of TSS, if you know, TSS is simply ESS plus RSS, right? Now ESS will be then what? TSS minus RSS, right? TSS minus RSS. TSS is given to you, this. And RSS, you just found that out. So what will be, if you take subtraction, 105.1188 minus this RSS is 9.830172. So ESS will come out to be 95.288628. Right? So this will be the value of ESS. So you have the value of ESS, you have the value of TSS, take the ratio, this upon TSS, 105.1188. If you do that, this will come out to be 0.906485, something, something. So approximately, if you look at this, 0.9065 approximately. And this will be option number B. See, 0, this is the closest, 0.9065. This will be the answer, right? So this is about all from my side for this video. I hope you like this video. And if you have any questions anywhere from the questions that we have discussed today, you can let me know. You can comment down below and I'll reply to that definitely. And I'll share this PDF. You will get this PDF in the Telegram group. If you want, you can take a look at this, solve these questions by your own, and revise all the important concepts that I have touched upon this, right? And in the next video, we'll also continue with this discussion. We will go into time series. We'll focus on time series and the rest of the topics that we have not covered in this video. So stay tuned for that. And I wish all of you all the very best. I hope all of you will do very well in your exam. And stay tuned for the next video. Thank you for your time.